So now we can talk about the space environment, the meat of this lecture. We're going to be talking about physical phenomena. So here are a list of physical phenomena that we see in space. And this picture that I have here is where I think these physical phenomena originate from, the four fundamental forces of nature. So something that I really enjoy about space is our ability to experience many fundamental forces of nature more directly, and also in different degrees, as these four interactions are more prevalent in a space environment. Physical phenomena that exist in the space environment are specific instantiations of the four fundamental forces of nature: gravitation, electromagnetism, weak and strong interactions. The link to gravity is rather clear, gravitation to gravity. If we talk about electromagnetism, we can break it down into concepts of electric forces and magnetic forces. This links to magnetic fields and electromagnetic radiation. And then also plasma produces magnetic fields and electrical currents. The weak force, also called the weak nuclear interaction, is responsible for particle decay. And this is the literal change of one type of subatomic particle into another. Or more precisely, it can be in instances of cosmic radiation and solar wind particles, which are secondary particles that are created by this weak force. Finally, strong forces are what binds the fundamental particles of matter together to form larger particles. The strong interaction is something that we see in our everyday lives. It's what keeps structures and micrometeoroids together. It's the force that keeps matter together. Cool. Okay, so the first physical phenomena that I wanted to go into is gravity. Gravity is a fundamental force of nature that everything with mass experiences in proximity to another mass. As Newton once stated, every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. We are interested in the gravity imparted by planets, stars, or even small bodies on spacecraft. Gravity field strength varies by the mass distribution of the body and the altitude that the spacecraft is orbiting at, for which we'll just look at Earth as a case study. So if we were to stand in the middle of Earth, we would experience no gravity because our centroid is lined up with the centroid of the body. But if we were to stand at the surface of the outer core, we would experience a gravitational field strength of about 10.7 meters per second squared. Now, if we were to stand at the surface of the mantle or on a continental shelf, then we'll experience the very famous number 9.8 meters per second squared. So I'll just note here, the reason why the gravitational field strength between standing at the outer core and the upper mantle or the surface is different is because the Earth is denser at the core. So you're going to feel more of that mass in a more concentrated place, which creates a stronger gravitational field. Whereas the mantle is less dense, so that mass distribution is a little less dense, and we get a weaker gravitational field. Once we get into space, we've passed all of this significant mass, and this is where we can approximate the Earth as a particle with a static amount of mass. So once we gain some altitude, this is where the gravitational law, where you can assume the Earth is a particle. And so bodies at this altitude, let's say we are orbiting at 400 kilometers, which is where the ISS orbits and also where the space shuttle typically orbited. we would experience a gravitational field strength of 8.5 meters per second squared. Earth's magnetic field, also known as the geomagnetic field, is a magnetic field that extends from the Earth's interior out into space, where it interacts with the solar wind, a stream of charged particles emanating from the sun. The magnetic field is generated by electric currents due to the motion of convection currents of a mixture of molten iron and nickel in the Earth's outer core, as we were just talking about. As an approximation, it is represented by a field of a magnetic dipole currently tilted at an angle of about 11 degrees with respect to Earth's rotational axis, as if there were an enormous bar magnet placed at that angle through the center of the Earth. The North Geomagnetic Pole actually represents the south pole of the Earth's magnetic field, and conversely, the South Geomagnetic Pole corresponds to the north pole of Earth's magnetic field. So, fun fact. The magnetosphere is the region above the ionosphere that is defined by the extent of the Earth's magnetic field in space. This is a computer simulation of that magnetic field. It extends several tens of thousands of kilometers into space, protecting the Earth from the charged particles of the solar wind and cosmic rays that would otherwise strip away the upper atmosphere, including the ozone layer that protects the Earth from the harmful ultraviolet radiation. A schematic illustrating the relationship between motion of a conducting fluid organized into roles by the Coriolis force and the magnetic field the motion generates. So the pictures here are showing you how our magnetic field is generated by this molten core, by the this fluid dynamics of a molten metal, and then the outcome or the consequence is to experience a magnetic field with a shape like this. Next, I want to talk about the atmosphere. You can think of the atmosphere in space as more of a burden of particles to push through, producing aerodynamic forces. The atmosphere varies in air pressure and density, decreasing with altitude, and it can be broken down into 4 different layers. So the von Karman line, I'll just note, is at 100 kilometers. And this is where many engineers consider to be space. So the limit of our atmosphere is agreed to be at about 100 kilometers, the boundary between the mesosphere and the thermosphere. The atmospheric pressure at Earth's surface is about 100 kilopascal on Earth's surface, and at the von Karman line, it's about 0.02 pascals. That difference is about 5 orders of magnitude, or 1,000th of a percent of the atmospheric pressure at the von Karman line compared to on Earth's surface. So yeah, there are, I would say, 2 boundaries that we have to take into consideration. There's that von Karman line, but there's also the end of the exosphere. The Karman line is more so a rough boundary of space that separates fields of aeronautics and astronautics. I informally think of it as a line between where airplanes travel and where spaceships travel. When I think rockets, Blue Origin's, commercial space tourism flight, or Virgin Galactic's spaceship, they just need to make it past this line to say they were in space. But more formally, this is the altitude where aerodynamic lift is not as dominant as the centrifugal force. In principle, the exosphere covers distances where particles are still gravitationally bound to Earth, i.e. particles that still have ballistic orbits that will take them back towards Earth. The upper boundary of the exosphere can be defined as the distance at which the influence of solar radiation pressure on atomic hydrogen exceeds that of Earth's gravitational pull. So the edge of the exosphere is when you start to see particles either stochastically stay towards Earth or start to get pushed out of Earth's influence. This distance happens at half the distance to the moon, which is about 384 100,000 kilometers. The exosphere, observable from space as the geocorona, is seen to extend at least 10,000 kilometers from Earth's surface. So I think I answered this question about the upper limit of the atmosphere. And then there was a question, are CubeSats orbiting around the Earth in the thermosphere or exosphere? And absolutely, there is a huge density of satellites that are orbiting in the thermosphere, although more so above 300 kilometers. And then there are different bands of orbits that we can talk about, but I will save that for later. There's a rooster right outside, like literally right outside my window. Okay, so then this is a great transition into vacuum. As the atmosphere thins, we approach a region that is devoid of any matter. A pure vacuum, or a true vacuum, is a space completely devoid of any matter. But we use the term vacuum to approximate regions where there are significantly less particles zipping around. Here is a picture of an ultra-high vacuum chamber, which is common in chemistry, physics, and engineering, but maybe not at this size. These ultra-high vacuum chambers operate below 1/1,000,000th of an atmospheric pressure and can reach about 100 particles per centimeter cubed. Outer space is an even higher quality vacuum, with the equivalent of just a few hydrogen atoms per cubic meter on average in intergalactic space. These particles matter because they interact with spacecraft by bouncing off the spacecraft surface, which transfers charge or heat. Okay. Next, we'll talk about electromagnetic radiation. We've talked about this in the payload section, but it's also a concern that we have to think about in space generally, not just the frequency that you want to observe, but there's a ton of frequencies that are just constantly chattering in space. So if you were in deep space, i.e. a spot somewhere between galaxies, then the night sky would look a lot like the sky seen by astronauts in the ISS. When they look away from both the ecliptic plane and the galactic plane, minus the individual galactic stars. That is, it is like our deep sky photos in those directions that are dominated by galaxies, but no atmospheric distortions, no night skylines, and no zodiacal light. The spectrum is dominated by different things at different wavelengths, but basically it is the sum of the light of galaxies and perhaps intergalactic stars that escaped their galaxies. At long radio waves, it is dominated by supernova remnants and synchrotron radiation peaking between 1 and 10 megahertz. The millimeter band is dominated by the microwave background radiation at 2.7 degrees Kelvin. The far infrared is dominated by cold galaxy dust at 60 microns. The optical is dominated by galaxy thermal starlight at 1 micron, and the UV is dominated by hot stars at 0.2 microns. The X-ray spectrum from 3 to about 45 kilo electron volts is well fitted to some temperature model. And the spectral energy density from radio to X-ray is shown in this diagram. So you need to think about this kind of electromagnetic radiation as noise to the different kind of frequencies that you want to actually observe. These are perturbations or unwanted disturbances that you'll just have to account for. Okay, another form of radiation is high energy radiation. This can occur from galactic cosmic rays and also solar energetic particles. These ionizing particles are distinguished from plasma, which we'll talk about in just a little bit, based on their lower densities and higher energies. The main sources of energetic particles or ionizing radiation in space are protons and electrons trapped in the Van Allen radiation belts, cosmic or galactic ray protons and heavy ions from outside the solar system, protons and heavy ions from solar flares, and heavy ions trapped in the magnetosphere. So here I have a picture of the two types labeled galactic cosmic rays, which come out from galaxies far away. And then closer to us, there is the sun that is constantly spewing high energy particles and have specific events called solar particle events or coronal mass ejections. The sun dictates our space weather. And you can see that there is a heavy stream coming towards Earth for which some of the protection happens because of the magnetosphere. What's curious about our environment is that we have two radiation belts called the Van Allen radiation belts. The Van Allen radiation belt is a zone of energetic charged particles, most of which originate from the solar wind, that are captured by and held around a planet by that planet's magnetic field. Earth has two such belts, and sometimes others may be temporarily created, but these are the persistent ones. The inner Van Allen belt extends typically from an altitude of 1,000 kilometers to 12,000 kilometers above the Earth, and the outer belt from 13,000 to 60,000 kilometers. The trapped particles in the Van Allen radiation belts, as shown in the figure, include trapped electrons of an energy less than 7 mega-electron volts, which are easier to shield than the trapped protons with an energy of less than 500 mega-electron volts. The trapped proton energies vary approximately inversely with the altitude. So energies of 400 mega-electron volts are close to the Earth. The dose is affected by altitude and geomagnetic latitude. The radiation belts include an inner zone and an outer zone as compared in the table. So you see that the different types of high energy particles differ in the inner and the outer zones. It is generally understood that the inner and outer Van Allen belts result from different processes. The inner belt, consisting mostly of energetic proton, is the product of the decay of so-called albedo neutrons, which are themselves the result of cosmic ray collisions in the upper atmosphere. The outer belt consists mainly of electrons. They are injected from the geomagnetic tail following geomagnetic storms and are subsequently energized through wave-particle interactions. In the inner belt, particles that originate from the sun are trapped in the Earth's magnetic field. Particles spiral along the magnetic lines of flux as they move longitudinally along these lines. As particles move towards the poles, the magnetic field density increases and their longitudinal velocity is slowed and can be reversed. So it would move like so, reflecting the particles and causing them to bounce back and forth between the Earth's poles. So once it reaches here, it can bounce back and just keep doing, making that kind of orbit. In addition to the spiral about and motion along the flux lines, the electrons move slowly in an eastward direction, while the ions move westward. The gap between the inner and outer Van Allen belts, sometimes called the safe zone or safe slot, is caused by very low frequency waves, which scatter particles in pitch angle, which results in the gain of particles in the atmosphere. Solar outbursts can pump particles into the gap, but they drain again in a matter of days. The radio waves were originally thought to be generated by turbulence in the radiation belts, but recent work by James Green of Goddard Space, comparing maps of lightning activity collected by Microlab with data on radio waves in the radiation belts, suggests that they are actually generated by lightning from within Earth's atmosphere. The generated radio waves strike the ionosphere at the correct angle to pass through only high altitudes, where the lower ends of the gap approach the upper atmosphere. But this is still a working theory, and the results are under scientific debate. I will note, so I hope that answered the gap between the two belts. Now the question about when we send missions out beyond orbit, do they all have to travel through the belts? Is there any risk of danger? So yeah, I think it's safe to say that when we send missions outside of Earth's orbit, it does have to pass through these belts at some point. There is also radiation at the poles that we have to worry about, so there is no avoiding this radiation. And is there any risk of damage? Yes, definitely there is risk of damage from that high energy radiation. And I will talk about that later, but you're absolutely onto a good point. Okay, plasma. So the universe is made up of space plasma. A plasma is a gas that is so hot that some or all of its constituent atoms are split into electrons and ions, which can move independently of each other. Because they are made of electrically charged particles, plasmas can be strongly influenced by electrostatic and electromagnetic fields and forces, which can lead to very complex and interesting behaviors. Plasmas are found throughout the solar system and beyond, in the solar corona and solar wind, in the magnetospheres of the Earth and other planets, in tails of comets, in the interstellar and intergalactic media, and in accretion disks around black holes. So this stuff is ubiquitous. There are also plasmas here on Earth, ranging from the inside of a nuclear fission reactor to a candle flame. When matter becomes sufficiently hot and energetic, it becomes ionized and forms a plasma. This process breaks matter into constituent particles, which includes negatively charged electrons and positively charged ions. These electrically charged particles are susceptible to influences by local electromagnetic fields. This includes strong fields generated by stars and weak fields which exist in star-forming regions in interstellar space and in intergalactic space. Similarly, electric fields are observed in some stellar astrophysical phenomena, but they are inconsequential in very low density gaseous mediums. And then finally, we'll talk about cosmic dust and micrometeoroids. So there's a slight naming convention. Meteoroids are particles, these solids that are above Earth's atmosphere, but once meteors enter Earth's atmosphere, then they're called meteorites. So that suffix changes depending on where we find them. Cosmic dust, also called extraterrestrial dust or space dust, is dust which exists in outer space or has fallen on Earth. Most cosmic dust particles measure between a few molecules and 0.1 millimeters or 100 micrometers. Larger particles are also called meteoroids. Cosmic dust can be further distinguished by its astronomical location: intergalactic dust, interstellar dust, interplanetary dust, and circumplanetary dust, such as the planetary ring. Thousands of tons of cosmic dust are estimated to reach the Earth's surface every year, with most grains having a mass between 10 to the negative 16th kilogram and 10 to the negative 4 kilogram, or 100 milligrams. The density of dust cloud through which the Earth is traveling is approximately 10 to the negative 6 dust grains per meter cubed. Cosmic dust contains some complex organic compounds, such as amorphous organic solids with a mixed aromatic aliphatic structure that could be created naturally and rapidly by stars. A smaller fraction of dust in space is stardust, consisting of larger refractory minerals that condensed as matter left by stars. Micrometeoroids are very small pieces of rock or metal broken off from larger chunks of rock and debris, often dating back to the birth of the solar system. Tiny particles are a major contributor to space weathering processes. When they hit the surface of the moon or any airless body, the resulting melting and vaporization causes darkening and other optical changes in the regolith. Micrometeoroids have less stable orbits than meteoroids due to their greater surface area to mass ratio. And this is true for spacecraft too. Micrometeoroids that fall to Earth can provide information on millimeter scale heating events in the solar nebula. Meteorites and micrometeorites as they are known upon arrival at the Earth's surface, can only be collected in areas where there's no terrestrial sedimentation, typically in polar regions. Ice is collected, then melted, and filtered so the micrometeorites can be extracted under a telescope. So I have pictures of the different types of particles. We have this cosmic dust where the scale is 1 micrometer, and then this meteoroid. Oh, actually it's a micrometeorite because we collected it in the Antarctic, has a scale of 100 micrometers. Okay, and I think that I answered most of these questions, but there's a lingering question about the ozone layer. Just really briefly, the short answer is yes, commercial flight does impact the ozone layer, and in a bad way. Jet engine byproducts are bad. Who would have thunk? Here's a quote from David Fahey of NOAA. For 20 years, we have asked engineers to design engines that minimize production of nitrogen oxides. We regarded them as the main hazard from aircraft emissions. Now it seems aerosols of sulfur particles may be equally important. Okay, so just stop here if you want to unmute and ask a question. Okay, if not, then we're going to talk about how physical phenomena affect spacecraft. So given each of the physical phenomena that we just talked about, we're going to explore the effects on the spacecraft, call out any subsystem in particular that it affects, and then offer up governing equations if possible. For the assignment due next week, I'm asking you to look at the percent dominance of the different physical phenomena, where the governing equations are going to be very important for that assignment. All right, so let's revisit gravity. Gravity has this equation for force, where G is the gravitational constant, M1 and M2 are the masses of the objects interacting, and R is the distance between the centers of the masses. So M1 and M2 can be defined as either the planetary body. So in your cases, if we're doing a low Earth orbit, then Earth is the first mass. And then that satellite is going to be the second mass. R is going to be not only your altitude, but also the distance from the center of the Earth to the Earth's surface. So be sure to pay attention to that little nuance. You can also figure out the velocity of a circular orbit at some altitude, given this equation, where the orbit velocity is the square root of the gravitational constant times the mass of the planet, and the R, where remember, R is distance from center of planet to center of spacecraft. And then for closed orbits, we'll talk about orbits next class, but there are things called open and closed orbits. What you need to know about closed orbits is that the satellite comes back through to a circle or an ellipse. An open orbit is something like a parabola or a hyperbola. So for closed orbits, the spacecraft's orbital period is given by the formula given here, where all of the parameters have been explained. Oh, and just to go back, gravity affects the orbit that you're going to fly in, and it could also affect your attitude control system. There are things called gravity booms that you can take advantage of this phenomenon. Magnetic fields affect the attitude control system. So the relevant equations that you should know say that you have a magnetic dipole generated by a magnetorquer, shown in this picture. Given that you are in a magnetic field, you can produce a resultant force in this direction. To do so, your magnetic dipole is dictated by this equation, where your dipole is equal to the product of the number of turns in a wire, the current provided, and the vector area of the coil. So the vector area is this cross-sectional area, which is a circle here. The dipole interacts with the magnetic field, where B is that magnetic field, and the torque is defined as magnetic dipole cross the magnetic field. That cross product is why you'll see that the resultant force or torque is out of the plane of the direction of the magnetic dipole and the magnetic field vector. Something you can use to your advantage is that we know what the magnetic field of the Earth looks like. We've characterized it. And so if you put some kind of internal magnetic field to the spacecraft, you can align your spacecraft's attitude with the magnetic field. If you had many different magnets inside of your spacecraft that are in the 3 orthogonal directions, there's something called 3-axis control, where you could control your attitude in all 3 degrees of freedom, and you wouldn't be limited to just following the magnetic field in one direction, as this is doing. So you will learn about that in the Attitude, Determination, and Control subsystem chapter. The magnetic field also affects our command and data handling subsystem. The geomagnetic field influences particle motion in the Earth's orbit, and it deflects some particles from interplanetary space. So in this case, the magnetic field helps spacecraft's health. The geomagnetic field would have a dipole shape, except for the solar wind that distorts the geomagnetic field into a parabolic shape. So you can see this solar wind pushing this geomagnetic field into this interesting shape. And we talked about earlier how the magnetic field traps charged particles. The magnetic field is strongest at low altitudes. The dipole field geometry results in a region known as the South Atlantic anomaly, which is not labeled here, but previously there was this little blip over the South Atlantic where spacecraft are subject to more radiation. And it's an anomaly because there was just a little notch. When spacecraft pass over that point, it's just this localized area where they're subject to more radiation. Yeah, so this is just a diagram of the Earth's magnetosphere. Okay, to talk about atmospheric pressure and temperature, this affects the spacecraft's thermal subsystem. So let's walk through this diagram. One of the questions was, how does the temperature change with respect to altitude? And so you can see the temperature change is continuous and rather gradual. Also note that the amount of temperature that changes is really not that much. It ranges between, let's say, negative 85 to 40, 30. So if you follow the temperature change upwards from our surface, temperature decreases because of atmospheric thinning. But in the stratosphere, temperature increases because of energy absorption of ultraviolet radiation. And then it decreases again because of the thinness of the atmosphere and a lack of ozone. And then temperature increases due to absorption of shortwave radiation. And how does a spacecraft deal with this change? I'll just note here that not many spacecraft fly in this region. Most burn up within this region or have burned up at this point. But when it comes to the mesosphere and above, where spacecraft do fly, I'll talk about how vacuum affects the thermal subsystem. Atmospheric drag is a phenomenon that is experienced by spacecraft at different altitudes. Despite the atmosphere being thinner, the atmosphere still is a dominant effect in a spacecraft's orbit. So there's a phenomenon called atmospheric drag, where the equation of motion, the equation for force, is given here, where the force of drag is equal to half times the coefficient of drag times the area. So this is the area that is being hit, the face that is being hit by atmospheric particles. It's perpendicular to the velocity vector. Then rho is the atmospheric density, and v is the velocity. So you have to know these different parameters: pressure, density, temperature, orbital velocity, and spacecraft area to get this drag force. And the outputs, you can also get orbital velocity by integrating drag into equations of motion, which is important for orbital dynamics. And then there was a question about orbital lifetimes in the earlier part of this semester, where you can see here, there are initial orbital altitudes that spacecraft are ejected into. But because of atmospheric drag, the spacecraft's orbit decreases in altitude little by little until the spacecraft re-enters the atmosphere. That re-entry dictates the end of an orbital lifetime, which can be determined here generally with your initial orbital altitude and your mass to area ratio. So mass divided by area, if you have a more spherical body, something that has, something that has less area, so you're a more compact thing. If you're more compact, then you would be red. So more spherical, compact spacecraft will have longer orbital lifetimes. But if you had something with a high area, so like a sail, where A is very large, then you would follow some kind of path like the yellow, where your orbital lifetime is going to be much shorter, even if you started at the same altitude as that sphere. So that's some intuition behind atmospheric drag and how it affects not only your attitude, but also your mission architecture. Okay, as we were talking about re-entering the atmosphere, objects entering an atmosphere experience atmospheric drag, which puts mechanical stress on an object, and aerodynamic heating, caused mostly by the compression of air in front of an object, but also by drag. These forces can cause loss of mass, which is called ablation, or even complete disintegration of smaller objects. An object with lower compressive strength can explode. For Earth, atmospheric entry occurs by convention at the Kármán line at an altitude of 100 kilometers above the surface, while, for example, at Venus, atmospheric entry occurs at 250 kilometers. Every object in Earth orbit below the 1,000-kilometer altitude is subject to atmospheric drag, which will decrease its energy and slowly reduce altitude in a spiral that will eventually cause it to re-enter the Earth's atmosphere. Objects with an initial altitude of 1,000 kilometers may take centuries to complete this process. However, objects at 500 kilometers will normally decay within about 10 years. And the average object at 200 kilometers will decay within a very few days. Uncontrolled objects reach high velocities while accelerating through space toward the Earth under the influence of Earth's gravity and are slowed by friction upon entering Earth's atmosphere. Various advanced technologies have been developed to enable atmospheric re-entry and flight at extreme velocities. An alternative low-velocity method of controlled atmospheric entry is buoyancy, which is suitable for planetary entry where thick atmospheres, strong gravity, or both factors complicate high-velocity hyperbolic entry, such as the atmospheres of Venus, Titan, and gas giants. So here I have a picture of a satellite re-entry where the point is for the satellite to disintegrate. This is the fate of many cube satellites, many low Earth satellites for that matter. And then on the right, there is an artistic rendition of the MER aeroshell, which is supposed to survive entry, descent, and landing. In either case, the atmosphere determines thermal profiles that the spacecraft will experience, and also the mission lifetime, as we talked about in the last slide. Okay, so the vacuum, as we were alluding to earlier in the atmosphere slide, a vacuum affects the thermal subsystem of a spacecraft as it's insulative to convective heat transfer. Here you'll see a diagram of the major heat transfer methods in space, where radiation is the dominant heat transfer method. There are different sources for radiation, such as the sun, the reflected sunlight from the Earth, which is albedo, and then outgoing is the spacecraft's heat transfer to just black space. That kind of transmission and shedding of heat because space is very cold, that 3 Kelvin degree cold. But the spacecraft also radiates to and from Earth, which is a thermal body. So you can think of thermal bodies interacting with other thermal bodies through this mechanism called radiation. So that's the external transfer. If you think about heat transfer internally to the spacecraft, that is dominant to, conduction is the dominant form of heat transfer within a spacecraft. I got a question about why is this a problem for spacecraft? And I wouldn't necessarily say that it's a problem, but it's just a different frame of thinking for how heat transfer happens. Because most of the interactions on Earth, because we have a dense atmosphere on Earth's surface, we usually think about heat transfer as convection and conduction. So it's not that it's a problem, it's just a different way of solving the heat transfer problem. Okay, this is a busy slide, but the thing that you need to take away from it is that high energy radiation and plasma really messes up your electronics, which is important for command and data handling. When a single high energy proton or ion penetrates a satellite surface and encounters an electronic device, it may decelerate and lose energy through an ionization process. This results in a short pulse of current in the impacted device, known as a single event effect. There are 2 different types of errors. There's a hard error and there's a soft error. The damage can be, for soft errors, the damage can be temporary and non-destructive. This includes events like a single event upset, which is just a bit flip. So say you have a wire transmitting data, one of the bits in the data can just be flipped. There's something called a single event latch-up, which is a potentially destructive condition where a component draws excessive current, which basically means a short to ground. There are hard errors, which are permanent and functional in nature. These include single hard errors that cause a permanent state change, such as a stuck bit in a memory device. There are things called single event burnouts, which are non-reversible device failures due to a high current state in a power transistor. And then there are single event gate ruptures, a destructive rupture of a gate insulator. Spacecraft really don't like high energy radiation. So spacecraft engineers try to avoid high points of solar activity for mission operations. Sometimes you can't help it, so fault tolerance is built into the flight software to reboot the spacecraft if, for example, a coronal mass ejection blasts through the spacecraft. Hopefully, the electronics are not totally fried. One way that you can protect against these kind of events is to protect your electronics within a radiation resistant box, whether by putting just as much mass as possible between the space environment and your electronics by having like thick metal cages or surface coatings. So yeah, you'll see here there are many different radiation sources. They can be broken down into particle types and then the primary effects in the devices, which will be expanded upon in the command and data handling section. Okay, let's see, I have 3 slides left, so I'll just blast through this. Plasma, as we were talking about earlier, are really hot particles, and they can exchange charge and heat with spacecraft. They can affect an orbit. They can also affect your electrical power system and all the other electronics that you have on board. So there's something that can happen in space where if plasma runs over your spacecraft and your spacecraft develops or accumulates charge, there can be a electric potential differential between, say, a spacecraft wall and your electronics. When this happens, there is a possibility of an arc, or as you would think in nature, like a lightning bolt that connects some high potential with a lower potential, and that creates something potentially catastrophic. It could be like electrostatic discharge, or it can be like this sustained arc on this board. So that could be pretty explosive. Either way, it is very scary to have potential differentials between different parts of your spacecraft. So electrical engineers will have some common ground between the boards and the spacecraft walls to make sure that kind of differential doesn't occur. There's also something called Lorentz force, which is, so say again that your spacecraft accumulates charge, and say that you are within a magnetic field. This accumulated charge will impart a Lorentz force on the spacecraft. This Lorentz force is given by F is equal to Q, which is the spacecraft charge, times your velocity cross with your magnetic field. So you'll see here just like a free body diagram that your Lorentz force does change your velocity vector a little bit. So that kind of small change is like a perturbation force, where perturbation is an unwanted response. Some spacecraft engineers have designed missions such that the Lorentz force is not just a perturbation, that you can actually create a mission around a Lorentz force to augment your orbit. Yeah, so cool space phenomenon. The last thing that I want to talk about before I leave are high velocity impacts. As we were talking about, there are different particles in space that can impact your spacecraft, and they can do, destructive damage as much as erosion to penetration to catastrophic events. There are a distribution of different sizes of particles in space. It also depends on the altitude. So I just want to focus in on this little snapshot. Say that we were orbiting at 400 kilometers, which is the ISS. The probability of collision per year while you're up there is about 0.001%. So it's 10 to the negative 5. So although it's not a very big concern, you'd still like to protect against it because we are risk-averse engineers. Okay, so I don't have much time left, but I would like for you in your assignment to discover the dominance of different physical phenomena in their regimes. Here's just a snapshot of the different torques, and as you raise with altitude, the prominence of these different phenomena vary. Okay, so I will stop now. Stop.